Hello BC Calculus students, this is Mr. Johnson and this is section 3.4 in our notes, and this is example 10. I'm going to try a slightly different approach here because what I'd like to do is walk you through all of the calculator keystrokes for this particular problem, but I'm having difficulty with being able to write that as well as project the calculator. So what I'm going to do is actually walk you through the solution guide from AP, and then I'm going to walk you through how to calculate all of this stuff on your calculator. So that's the approach we're going to try for this example. So in example 10 in your notes, this is on page 19, we have the third FRQ question for the BC exam from 2010. And it's all this particle motion stuff that we've begun to talk about. And so that formula sheet that's in your notes that I discussed in the previous video, that's obviously really important for this type of a problem. So what we have is a particle that's moving along a curve so that our particular position is given by x of t, y of t. We're given the x of t equation explicitly, so t squared minus 4t plus 8, but the y of t equation is not given to us. Both x and y are measured in meters and t is measured in seconds, and we do know that dy dt is equal to t times e to the power of t minus 3 and then subtracted by 1. And so we know y prime, but we do not know y of t. So for part A, we want to know the speed of the particle at time 3 seconds. Now again, I am showing you the answer key here so that I can walk you through typing this into your calculator. But the speed equation is going to be the square root of the dx dt squared plus dy dt squared, and we are substituting in 3. Now in your calculator, what I would suggest is to type in the equations that we're going to use throughout the problem. Now we're going to often use x prime of t, so what I've done is already typed in x prime of t, which I just did using the power rule, so 2x minus 4. If for some reason maybe that derivative is too difficult to do by hand, you could always use math 8 and do a derivative here, just a variable derivative in y1. But again, this is my x prime or my dx dt. This is my y prime or my dy dt. And I have them stored right now as y1 and y2. Some of you have seen this before, others of you have not. So when we type this into our calculator, we're going to take the square root of the dx dt equation, which I have stored as y1. And the easiest way to do this is first put parentheses and then put alpha f4, and you can call up y1, and then we do need to substitute in 3 for the input. So we're going to use function notation to do that. Make sure you have the correct parentheses, but that 3 is now inputted into that equation. And then we simply just add parentheses the y2 equation, so alpha f4, and then y2, and again we're substituting in 3 for the input, and we are squaring that as well, and that's all there is to it. So our calculator can do so much of this work for us, and instead of inputting in the entire equation and substituting in 3 every single time, this is often a much faster and more accurate approach. Now keep in mind that you need to round to 3 decimal places, so you get 2.828. They do not ask for units, but you're welcome to put them down, but you're not going to get any credit for them. Okay, for part D, we're going to do the total distance. This is another formula that you must memorize. The total distance will be the integral from 0 to 4 in this case of the square root of dx dt squared plus dy dt squared. So essentially what we're doing is we're integrating the equation for speed over the interval. Remember, that's going to be in math 9. So math 9 is the definite integral. We're going to go from 0 to 4. And then we're going to take the square root of, now this time we're not substituting in any values, so we're simply taking y1, so again it's alpha f4 squared plus alpha f4 and y2, and we're squaring that. And then of course you need your dx. Remember, we're in function mode here, so everything is in terms of x. Obviously this is all in terms of t, but these are just dummy variables, so don't somehow put a t in there. That will mess up the calculator. And then if you hit enter, you get your answer. Now keep in mind, 3 decimal places you absolutely need. You could put 0.587 or 0.588 is fine as well. Again, you do not need the units. Okay, moving on to part C. We want to find the time in between 0 and 4 when the line tangent to the path of the particle is horizontal. Now, what we know with a horizontal tangent line is that the slope of that line is 0. So notice in the solution guide it says dy dx is equal to 0. Now, dy dx is the same thing as dy dt divided by dx dt. This is necessary for any kind of pointing on this particular problem. You must have this statement down. Otherwise, you're not showing the reader what you're actually studying. Okay? You're not showing the reader what you're actually trying to find. Now, if we have a horizontal tangent line, keep in mind that this particle is moving horizontally. It is not moving vertically. So that implies that dy dt is 0 because we're not moving vertically. Dy dt is going to track the motion vertically, while dx dt is tracking the motion horizontally. So we are moving horizontally, but we are not moving vertically. So therefore dy dt is going to equal 0, but dx dt must not equal 0. If they both equal 0, that means the particle is completely stopped. But again, the question is asking for a horizontal tangent, which means that this particle needs to move horizontally, which means dx dt needs to be something other than 0 so that it's actually moving, and dy dt is equal to 0, which means it's not moving up or down. So what we're going to do is we're going to solve this equation using our calculator. We're going to figure out what t value allows us to get a dy dt of 0. Now keep in mind, in my calculator, in y2, I have my equation that I'm analyzing. I'm going to go up here. I don't want to clear my first equation. I simply just want to get rid of it graphically. So I'm going to go up to the equal sign for y1 and hit enter. And what that's going to do is it's going to get rid of that graph on my screen when I go to graph it. It's just going to keep it stored there, but it's not going to graph it itself. Then what I'm going to do is go to my window and go from 0 to 4 because it tells me that I'm analyzing the interval from 0 to 4. Last thing I'm going to do is go to zoom, and I'm going to go to zoom all the way down here to 0, which is called a zoom fit. And what it does is it kind of tweaks my window to make the graph look as nice as possible. It does not work 100% of the time, but if you set your window for x, like in this case 0 to 4, and then you do a zoom fit, it often will fit the y values really nicely to what you're looking for. So we're clearly looking for the x-intercept here, the solution to that equation that we're talking about. So we're going to go up to second and calculate, and we're going to choose option 2, which is the 0. Now, some of you have done this where you've scrolled along the graphing calculator, or excuse me, the graph itself using your arrows in the graphing calculator. What I'm going to do is just take a look at my values. I know this x-intercept is between 2 and 3. So when they're asking for a left boundary, I'm just going to simply type in 2 and hit enter. It's going to give me a boundary. I'm going to type in 3 and hit enter. It's going to give me another boundary. Essentially, I'm telling the calculator that the x-intercept is between these boundaries. And as for a guess, I'm just going to hit enter because I'm close enough there. And you get 2.2079. So your value here, again, is 2.20794 is how they have it listed in there. Okay. Now the question says, is the direction of the motion of the particle towards the left or the right during this time? Now remember, we confirmed that dy dt is 0, which means we're not moving up or down, but we are moving horizontally. And the way we track horizontal motion is that we take a look at the dx dt value at this particular moment. Now keep in mind with your calculator, your x value is here. I'm gonna press second and quit, and I'm gonna just simply type in x and hit enter. You'll see that it's the exact same number I just had on my screen. It's a storage unit. So I would like to calculate alpha f4 y1. Oops, I'm sorry, alpha f4 y2. Oh, nope, I back it up. Let me rephrase here, sorry. We're going back to alpha f4 y1 because we want the dx dt, which is y1 for me. And then I'm going to simply plug in this value for my input. And that gives me my dx dt, which they do not list in their solution guide, as you can see, but this value is positive. So what does that mean? So if dx dt is positive, then our particle is moving to the right at that particular time. Okay, and you can see in the scoring guideline how those points are distributed. Okay, let's move on to part D. So with part D, it says that there's a point with x-coordinate 5 through which the particle passes twice. So keep in mind that you have this random point in space where x is 5, and the particle kind of travels around, and then it comes back to that point. So there are 2 instances when the particle passes through that particular point. We're trying to figure out in the first part of this, part D, the 2 values of t for which this occurs. So again, what we're looking for is when x is 5, we want to know the 2 values of t for which that occurs. In the scoring guideline, they put x of t equal to 5, and they just simply make the statements 1 and 3. I'm going to show you how to get those. So we have our 2 different equations. I'm going to now enter in the x of t equation because I didn't have that one before. So x squared minus 4x plus 8. And I'm going to go up to my second equation, and I'm going to take away the equal sign, because what I'd like to do is figure out when this particular equation is equal to 5. So I'm going to graph my equation of x of t, I'm going to graph 5, and we're going to figure out when this occurs. And my window, keep in mind, is still 0 to 4. So we go to zoom and go to option 0, which remember that's zoom fit. And it allows the calculator to work through the nicest looking window. You can see there's 2 instances. They look like very nice values. They should be 1 and 3. We can go to second calculate. We can go to option 5, which is intersection. And it's asking for the first curve, which right now I'm on the parabola, so that certainly could be my first curve. Second curve, now I'm on the line. Sure, that's fine. And then my guess, all right, there we get 1. We could go through the same process, and we will get 3. So there you go. So you have your 2 intersections there. You can also do this one by simply taking 5, setting it equal to our equation for x, and then solving for t by factoring. Setting it equal to 0 and factoring is probably just as fast, if not faster, than doing it on the calculator. But anyway, so we get 1 and 3. Okay, so the question says, find the 2 values. Okay, that part is done. The slopes of the lines tangent to the particle's path at that point. Remember, slope, as we discussed in part C, is dy dx, which is the equivalent of dy dt over dx dt. So that's a formula we need to know. We want to just simply calculate that at 1 and at 3. So the way we're going to do that is go back to our main screen here, and we have in y1 we have dx dt, and in y2 we have dy dt. So I'm going to take alpha f4, and I'm going to take the equation 2, which is dy dt, and I'm going to plug in 1. And then I'm going to divide by, and then alpha f4 y1 evaluated at 1. And this gives me my slope at 1, which you can see on the answer key is 0.432. And then I'm going to do the same thing, except I'm just going to go up here and cheat a little bit. I'm going to hit enter and go in here and just simply change my values to 3. And when we do that, we get 1. So there you go. That's going to be the 2 slopes at those points. Okay, the last question asks us to find the y-coordinate of that particular point, given that y of 2 is equal to 3 plus 1 over e. So again, keep in mind with this particular problem that we know dy dt, we know one little value on y of 2. We need to figure out either y of 1 or y of 3. They're the same thing, right? It's just the same point. So we could do, again, either y of 1 or y of 3. They're the same. And we're going to utilize the fundamental theorem of calculus. So if we integrate this particular definite integral from 2 to 3, it is going to be equal to y of 3 minus y of 2. And so we're utilizing the fundamental theorem. We know that y of 2 is here, and if we add the change in y from 2 to 3, then we will get y of 3, or where y of 3 is. Because remember, you could think about it this way as well. If this is y of 2, this integral is going to calculate the change in y during that little interval there, which gives us then the result, which is y of 3. So in your calculator, you have 3 plus 1 divided by e. Just going to do e to the first. I don't even see where my button is there. And then plus math 9, which is from 2 to 3 of alpha f4 y2 and then dx. And we get 4. So this is, again, this is example 10 in your notes for section 3.4, and I hope it was helpful to see some of the work on the calculator along with how AP scored this particular problem in 2010. Thank you.